In today's lesson, we are going to be taking a look at limits that involve infinity. That means it could be as x approaches infinity or negative infinity, or as the limit itself goes to infinity or negative infinity. Here in example 1, we see a function 1 over x minus 1, and here at x equals 1, we're running into something strange. So some of you may know this as a vertical asymptote. But if we wanted to describe the behavior, what's going on at x equals 1, well, here from the left, it looks like f of x is just plummeting down towards negative infinity. If we look at the limit from the right, it looks like it's going to skyrocket towards positive infinity. So these are the type of examples that we're going to be taking a look at today. If we try to approach this function like we have in the past using limits, we can always fill on a chart like this one. So let's do that. If I want to take the limit coming from the left, I could start with 0. So if I plug in 0, I'll get 1 divided by negative 1, which is negative 1. If I plug in 0.5, I'll get 1 divided by negative 0.5, which is negative 2. Plug in 0.8, that's going to be 1 divided by negative 0.2, which should give us negative 5. If I plug in 0.9, that will be 1 divided by negative 0.1, which gives us negative 10. 0.99 would give us negative 100. 0.999 would give us negative 1,000. And 0.999999, I believe that's going to give us negative 1 million. And then if we just keep plugging in 9s, you're going to see that this is really trending towards negative infinity. All right, so what if we try to take a right-handed limit? So if I plug in 2, well, I'm going to get 1 divided by 1, which is 1. Plug in 1.5. I'm going to get 1 divided by 0.5, which is 2. And then I'll get 5, 10, 100, 1,000, 1 million. And if I keep going, it's going to be heading towards infinity. So this is our first example of really seeing infinity come up. And this is kind of how we're going to go about it. We'll see some shortcuts and some rules going forward, but this is the general principle we're going to be using. What happens as we get closer and closer and closer to a number? Here we have our first theorem about vertical asymptotes. So this theorem says that if a function f is a quotient of two other functions, n and d, if the function d at point C is 0 and n is not 0, then we would say that there is a vertical asymptote at x equals c. So what they're really saying is that if you've got a function divided by another function, if a particular value of x makes the denominator 0 while the numerator remains non-zero, then we run into a vertical asymptote. So for example, if I've got f of x equals x squared plus 1 divided by x minus 1, if I want to take, let's say, if I want to take a look at x equals 1, if x equals 1, my numerator is going to be 2, and my denominator would be 0, meaning there is a vertical asymptote at x equals 1, because the numerator is not 0, and the denominator is 0. Here in example 2, they ask us to find the vertical asymptotes if there are any. So remember, for a vertical asymptote, we need the denominator to be 0. So that's going to be our first step. Figure out when is the denominator 0. So x squared minus 1 equals 0. Add 1 to both sides, and we're going to get x squared equals 1. Take the square root, and we're going to get that x equals plus or minus 1. Now, this is probably where most people will make their mistake. They'll just say that the square root of 1 is 1, but we need to remember that -1 is also a potential solution here. Now, that is our first criteria, that the denominator is 0. But now we need to check the numerator. So let's see what happens at f of 1 and at f of -1. So if I plug in 1, in the numerator I'm going to get 1 plus 1 minus 2 divided by 1 minus 1. So I'm going to have a 0 over 0 there. If I plug in -1, I'm going to get 1 minus 1 minus 2 over 1 minus 1, which is going to be -1 over 0. So if we take a look, 0 over 0, it means we're going to have some kind of cancellation. So I'm going to take a look at this one in just a second. But if I look at f of -1, I get -1 over 0. So this is absolutely a vertical asymptote. I have a non-zero over 0. So if I want to take a look at f of 1, it means that x minus 1 has to be a common factor of both the numerator and the denominator, which if we take a look, we'll see that's true. The numerator would be x minus 1 times x plus 2. The denominator would be x minus 1 times x plus 1. So we do have some cancellation here. And that will tell us that this is really x plus 2 over x plus 1. If I try to plug 1 into this new function up here, I'm going to get 3 over 2, meaning no vertical asymptote for f of 1. So my only vertical asymptote would be here when x equals -1. Example 3. Again, we're being asked to find the vertical asymptote if there is one. So for this problem, we're trying to take a look at the denominator. We want to know, where is the denominator going to be 0? So x squared minus 4x plus 3 equals 0. So I'm going to have to factor. So I need two numbers that multiply to be 3, but add to be -4. So this should be x minus 3 and x minus 1. -3 times -1 is +3, but -3 plus -1 is -4. Now, if I go back to my original function, f of x, get x minus 3 over x minus 3 times x minus 1, we're going to notice that there's actually already a cancellation of the x minus 3. So the real function that I'm looking at is going to be 1 divided by x minus 1. So what value of x makes x minus 1 0? Well, that is going to be that x equals 1. So x equals 1 is the number I'm going to be looking at. If I plug in 1, I should get f of 1. This should give me 1 over 0. And 1 over 0, 1 is not 0, and 0 is 0, so this is a non-zero divided by 0, meaning I have a vertical asymptote here. Here we've got another vertical asymptote problem. So we're going to take a look at this one just like all the others. We're going to take a look at the denominator and set it equal to 0. So we've got 5 times x minus 2 squared equals 0. Now I can divide both sides by 5. And I'm going to get x minus 2 squared equals 0. Take the square root of both sides. I'll get that x minus 2 equals 0. And I'm going to get that x equals 2. So this is my only candidate for a vertical asymptote. So let's see what happens if I plug in. Let's take a look at f of 2. I'll get 2 squared plus 20 divided by 5 times 2 minus 2 squared. So this is going to be 24 over 5 times 0 squared. So this is 24 over 0. 24 is not 0. 0 is 0. So this is a non-zero divided by 0. meaning my vertical asymptote would be at x equals 2. That would be my final answer. Let's take a look at limits at infinity. So this is when x is going to be approaching infinity or negative infinity. So it says that if p is a positive real number and k is any real number except for 0, then the limit as x approaches negative infinity of k divided by x to the p is 0. So this would be like, because k is any real number, so let's say it's 5. And then p is a positive number, so let's say we've got, let's say x to the third. The limit as x approaches negative infinity of this guy right here would be 0. For number 2, they say the limit as x approaches infinity of k over x to the p would also be 0. And we're going to take a look at some of these examples on the next couple slides. Number 3, they say that the limit as x approaches negative infinity of k times x to the p will be plus or minus infinity, depending on some of the values here. And then number 4, the limit as x approaches infinity of kx to the p is also plus or minus infinity, depending on some of our signs. Continuation of limits at infinity, we've got theorem 3 here, and this is talking about taking a limit when we have a large polynomial. So they say that p of x is a sub n x to the n plus a sub n minus 1 times x to the n minus 1, all the way down until we get a sub 1 of x plus a sub 0. So this might be confusing, but they're really talking about is if we take a polynomial and let's say we start with something like 3x cubed and plus 4x squared plus 7x minus 30. Something like this. So we've got polynomial in descending order. Our x cubed is first because it is the highest degree. And then we've got x squared, 7x minus 30. So they say, given this setup, the only numbers that we really need to look at is the leading term. So they're saying the limit as x approaches infinity of p of x is really the limit as x approaches infinity of the largest term. And this might seem familiar from algebra. We know that the highest degree here actually dictates how the function will look. So we know that if this was a square, we'd be getting a parabola shape. If it's a cube, we're going to get a cubic. If it's a fourth, again, we're going to get a U. And in the middle, we'll have something going on. But for the long-term behavior, it really just looks at the highest degree of the polynomial. And that's what they're talking about here. So we will see a bunch of examples like this, but it should look familiar to some of the algebra 2 that we've done. In example 5, they say find each limit. So finding each limit. So my highest degree here is really just my 2x cubed. So what I'm really looking at is the limit as x approaches infinity of 2x cubed. Well, I know from the previous theorem that this should be plus or minus infinity depending on the values. And I would argue that this has to be positive infinity. Mainly, we're talking about bigger and bigger and bigger numbers. So clearly I'm talking about positive numbers. 2 is positive times a positive number cubed is going to be positive. So as x gets bigger, the function is going to head towards positive infinity. Well, here in example 6, it looks like we lost our limit, but I'm going to guess that this is the limit as x approaches infinity. So if I take a look at a, the largest term here is my 3x cubed. So the limit as x approaches infinity of 3x cubed, well, that's going to be positive infinity. 3 is positive, and a large number cubed is also positive. So this will be positive times a positive, which is positive. For b, don't get tunnel vision. We have negative 500x to the fourth as our largest degree here. So this should boil down to the limit as x approaches infinity of negative 500 x to the fourth. Now, if I take a really large number and I raise it to the fourth power, it's going to be positive, but negative 500 is negative, so negative times a positive is a negative, so I'm going to get negative infinity. Horizontal asymptotes. So we already took a look at vertical asymptotes. The other type of asymptote that we're going to deal with are called horizontal asymptotes. And depending on what class you take, you might see something called a diagonal asymptote, but we don't really deal with those at this level. If you're in a class that is dealing with diagonal asymptotes, it's going to be using the same rules here. And if you've got questions, you can always feel free to message me about it. But for the meantime, we're just going to deal with the horizontal and vertical asymptotes. So this theorem says that if we've got two rational polynomials, so they're using a's in the numerator and b's in the denominator, they're saying that if I'm taking a limit as x goes to infinity or negative infinity, the only terms I want to look at are the ones that contain the highest degree in both the numerator and the denominator. So, for example, assuming that m and n are the largest degrees in both the numerator and the denominator respectively, then everything else in the polynomial is not really needed for the long-term behavior of the function. And if you're kind of confused about what a horizontal asymptote is, it's what's happening with the polynomial as x goes to infinity or negative infinity. It's the long-term behavior of the function. So they say there are three possible cases. If m is larger than n, so the degree in the numerator is larger than the degree in the denominator. Oh, they're going in the opposite way. They say if m is smaller than n, so if the degree in the numerator is smaller than the degree in the denominator, then we say that there is a horizontal asymptote at y equals 0. This would be something like x squared over x cubed. 2 is less than 3. Therefore, as x approaches infinity or negative infinity, we are going to get 0. Case 2, they say, well, what happens if m is equal to n? Well, then they say it's the ratios of the coefficients. So for 2, let's say I had 3x to the 4 divided by 7x to the 4. If I'm trying to take this limit, well, because they're both x to the 4, m would equal n, and I would just take a look at the coefficients, the 3 and the 7, and I would say that my vertical asymptote is 3/7. And then number 3, they're asking, well, what about, or they're talking about, what if m is greater than n? So the numerator is greater than the denominator. So this is like x cubed over x squared, kind of the opposite of number 1. Well, they're saying that if we're trying to take this limit, we're going to get positive or negative infinity depending on the signs of the coefficients. So in case 1, denominator bigger than numerator, horizontal asymptote 0. If the degrees are equal, we're going to get the coefficients, the ratio of the coefficients. And then number 3, if the numerator is greater than the denominator, this is where we're going to get infinity or negative infinity depending on coefficients. And then it's here in step 3. This is where the idea of a vertical asymptote, or not a vertical, but a diagonal asymptote comes from. So if you're in a class that deals with diagonal asymptotes, it's here in case 3, rather than saying, oh, it's infinity or negative infinity, you can do some long division of polynomials to figure out what type of function does it look like. Yes, it's going to infinity, but does it kind of look like an x squared, or is it more linear, like 3x plus 2? So again, for horizontal, that part doesn't matter. But if you're in a class that does deal with diagonals, it's case 3 that you would have a diagonal asymptote. Example 7, they say, find the horizontal asymptote if it exists. So here we just need to think of our horizontal asymptote rules. So remember, we need to identify what is the largest degree in the numerator and in the denominator. Well, thankfully for us, they are the leading terms of both the numerator and the denominator. So I'm really taking a look at the limit as x approaches infinity of 5x cubed over 4x cubed. Because these are both cubic functions, the horizontal asymptote is going to be the ratio of the coefficients, or just 5/4. Example 8 is very similar to example 7. They want us to find the horizontal asymptote, so that's saying the limit as x approaches positive or negative infinity. And here again, we need to identify what are the highest degrees in the numerator and denominator. And fortunately for us, they are the first terms. So I'm really taking a look at the limit as x approaches infinity of 3x to the 4th divided by 8x to the 6th. Well, x to the 6th is greater than x to the 4th, meaning the denominator is larger than the numerator. So this is going to be going towards 0. That was rule 1 on our previous slide with the rules. And now for our final example using horizontal asymptotes. They tell us to find the horizontal asymptote of this function. So again, we're going to take a look at the leading terms, or the highest degrees. So we got 2x to the 5th over 6x cubed. The numerator is greater than the denominator, so we know this will be either positive or negative infinity. And the way we can tell if it's positive or negative is by the coefficients. Here we have a 2. 2 is positive, and we have 6. 6 is positive. So these numbers are clearly staying positive. Positive divided by a positive is positive. If we were trying to go to like negative infinity, well, we'd get that x to the 5th is negative and x cubed is negative. Negative divided by a negative is still positive, so we're going to positive infinity no matter which direction we're looking. All right, so some closing thoughts on this section. So we've been taking a look at vertical and horizontal asymptotes. So vertical asymptotes, just to recap, it's where we are dividing by 0 and the numerator is not 0. So a number or polynomial divided by 0, we're going to find a vertical asymptote there. For horizontal asymptotes, there are 3 rules to remember. If the numerator is smaller than the denominator, so the degree in the top is smaller than the degree in the bottom, we are going to have a horizontal asymptote of 0. If the degrees are equal, so the degree in the numerator equals the degree in the denominator, then we take a look at the ratio of the coefficients. And then the last case is what happens if the degree in the numerator is larger than the denominator. Well, in that case, we are heading towards positive or negative infinity. And to determine which one it is, we just have to look at the sign of the coefficients. If the ratio of the coefficients is positive, then it's positive infinity. If it's negative, then we're going to negative infinity. Other than that, if you've got any questions, feel free to message me, and I'd be happy to go over anything. The homework is posted, so take a look at that, and good luck.